I've got another situation here for you to think about. You're welcome to pause the presentation here if you want to think this through on your own for a minute. We have a traveler again. He's traveling from point A to point B, and he's thinking about how many different possible ways he has to accomplish this. Right now, here, one thing that I want to emphasize to you about is that distinguishes this from a multiplication rule situation is that he's only making one choice. Right? He only has to choose one transportation method. And he has two different ways he can do that. One is by choosing a plane flight, and we're going to try using our tree diagram method here again to analyze this. So he has three different plane flights to choose from. And again, he's only making one choice. So I'm not going to start trying to branch here. And other options that he has are picking from among four different cars. And if we apply the same reasoning that we did when we were talking about uh, these itineraries in the last lecture, look at the total number of final branches here, and you'll get the total number of possibilities. So he has these three plane flights plus the four possible car choices for a total of 7 different ways that he can get from point A to point B. Okay, hopefully a relatively obvious result. The addition rule maybe isn't the most complicated tool we're going to have to work with here, but it is an important one. Right? There are going to be situations where the multiplication rule really doesn't get the job done, and we're going to need to combine it with this addition rule to get the final result that we're looking for. So the way the addition rule is usually stated is in terms of sets, right? So the way this works is suppose we have a finite set, right? That would be all transportation options, referring back to the previous example. And it's made up of a finite number of mutually distinct subsets. Right? Those are the different groups of options. So again, referring back to the previous example, one of these would be the set of all plane options, and the other would be the set of all car options. Obviously, they don't overlap, right? Cars and planes are distinct, right? And what this addition rule says is the size of the whole set is equal to the sum of the sizes of those distinct subsets. So we've got an example here for us to look at. And what makes this interesting, if you read through it here for real quick, is I don't know how many choices I have to make. Right? I may need to choose a 4-digit number, which I could do using the multiplication rule. Right? I've got my 4 options, and I have 10 digits I can put in each one. That would give me the number of 4-digit pins that I can create. But what about the 5s? Well, again, I could do that one too. 1, 2, 3, 4, 5. I could do that using the multiplication rule. 5 digits, 10 choices each. So these are the 4-digit words. These are the 5-digit words. Pins, not words. And finally, what if I have to choose a 6th one? The number of 6-digit words, pins, I don't know why I keep calling them words. The number of 6-digit words would be that many. All right, here's where the addition rule is going to come in. You notice that these are disjoint. Right? There are no 4-digit words in the 5-digit words. I don't know why I keep wanting to call them words. There are no 4-digit pins in the 5-digit group, and there's no 6-digit pins in the 4-digit group, and so on, right? So all 3 of these groups are mutually disjoint, and if I combine these 3 groups together, I get all of the possible options. And so this is exactly the kind of situation that the addition rule is designed to help us out with. The total number is going to be the sum of the number of ways we can do each of these individual sizes. All right, so what do I get here? This is 10,000, 1 and 4 zeros. This is 100,000, 1 and 5 zeros. And finally, this one here is 1,000,000, 1 and 6 zeros. And if we add all of those together, we get 1,110,000 possible pin numbers. Okay, so this is the kind of situation, if you're kind of trying to conceptualize in your head, when would I think about using the addition rule to answer a specific scenario? What you're looking for is a situation where you don't know up front how many choices you have to make. Right? If you find yourself in that kind of situation, that's where you say, okay, can I break this up, right? Like I did here, into individual scenarios where I do know how many choices I have to make. And can I do this in such a way that there's no overlap? Right? If I can, then I can just find the individual totals, the individual counts, add them all up together to get the grand total. So there was one really big caveat in that addition rule, and I referenced it repeatedly when we were working through that last example. Right? The one big caveat you have to keep in mind is that these individual groups of choices have to be disjoint. They can't have anything in common. And that kind of happened naturally in my examples. Obviously, if you look at the group of all 4-digit pins and the group of all 5-digit pins, obviously there's not going to be any overlap between the two. And it was the same with the travel choice. Cars and planes are different. Right? There's no possible overlap there. Well, what about when there is overlap? Right? What do we do then? And that's what we're going to talk about in the next lecture.